Thanks, Gary. Thanks, Ed. Hi, everyone. My name is Yeshwant Muthusamy, and this is me. I'm an AI technologist by day and a gourmet chocolatier by night. I've had technology leadership positions in companies that you see on the screen. These days, I'm back at my consulting firm that's called Yeshwant Solutions, where I help clients with their custom AI solutions, provide AI training and coaching, and do a lot of intellectual property advisement in various aspects of AI, including the expert witness. I'm currently the chair of the AI working group at the GBA, which is the Government Blockchain Association. This is just one more blowing up my own horn. And let's get right to it. Okay, in a nutshell, AI is transforming how we make decisions. We all know that, but it raises questions about transparency, model explainability, and so on. Blockchain creates trust through immutable records. Quantum computing is going to break the encryption that actually secures everything online. So we're going to be talking about the convergence of these three transformational technologies. And so the way I have this talk is I'm going to give a brief overview of each of these three technologies and then go into how they interplay or converge together or conflict in some cases. For people who are practitioners of one or more of these technologies, you might find a few of the slides too basic. Please bear with us. We'll get to the fun part. Okay, AI in plain English. You all know what AI is, right? So I actually have a lot more slides here, but since this group is knowledgeable, I've kind of condensed it down. It is useful to distinguish between the different flavors of AI. A lot of people tend to conflate AI with ChatGPT. There's a lot more to AI than just ChatGPT. Okay, so you have generative AI, which actually generates new data, which is very similar to its data set of training. You have discriminative AI, and then you have predictive AI. Data generation is only being done by generative AI. Discriminative AI doesn't generate any data, it categorizes it. This is the cat, this is the dog. And if you're using an iPhone and you have Face ID, that's an example of discriminative AI. This is Tom Allen. This is not Tom Allen. So it's things like that.
Things in there. You'll come back to
okay. And then you have predictive AI, which also doesn't do any new data generation, but predicts the outcome based on historical data. So you have the various use cases we all know and love, ChatGPT, Claude, Google Gemini, and so on. Speech recognition, image recognition, sentient analysis, or rather sentiment analysis, fraud detection. All those are examples of discriminative AI. And last but not least, predicting sales. I mean, your favorite realtor is using AI to say, based on the square footage and the location and other features of the house, what should the price of this house be with respect to all the others? And also, if you are from AT&T or Verizon or any of these service providers, you spend a lot of your time wondering about churn prediction. How many customers am I going to lose based on the number of irate calls that they made over the past month? So churn prediction is also using predictive AI. Given that everybody is all gung-ho about the new kid on the block, it's helpful to try and distinguish between generative AI and agentic AI. And the core function for agentic AI is autonomous action and goal-oriented behavior. And the focus there is taking initiative, making decisions, and executing tasks. Whereas here, it is to create outputs based on user prompts and data. your chat GPT isn't going to do squat unless you actually give it some input. So it is waiting for you to act. If you don't act, it doesn't do anything. Whereas here, you can give it a set of requirements and say, plan a vacation for me and my wife going to place X in the month Y. And I'd like to do all these things. That's it. It knows where to go, what seats to book. It does all those things. It might call, it might be one agent, or it can usually be an orchestration of multiple agents. Go and do the things. And if you leave with only one thought from this slide, it should be this one. Generative AI, by definition, is reactive. It's always going to respond to your input. Whereas agentic AI can be proactive. It's goal-oriented. It's got this built-in capability of reflection. Have I answered the user's request? Do I need to do more? Maybe I need to go back and do it once again. Do I get it right? So, okay. Now good. How many of you know what blockchain is? Keep your hand raised if you know what blockchain is outside of Bitcoin. First statement, I'm not talking about Bitcoin. I'm not talking about cryptocurrency. I'm not talking about any of the scrappy meme coins. That's me talking about blockchain technology. Right? And to prove my point, these are all the different use cases of blockchain. And there are too many, which is why you have the type so small. But we are going to focus on a few. This is where Bitcoin actually plays, banking, financial fintech. So Bitcoin is just one of many applications for blockchain. But we also have another area which is near and dear to us. Blockchain can also be used in the area of IoT, where IoT applications are feeding sensor data to the blockchain. And why would they want to do something like that? Because blockchain is used in transportation and logistics. There was a classic case study that was done between Maersk, which is one of the world's largest shipping company, and IBM. I mean, that was a study, but the one that I really wanted to mention was the blockchain pilot that Walmart did with IBM. Before they did this pilot, it used to take them over 3 or 4 days to determine the provenance of a box of sliced mangoes. And when they had an E. coli outbreak, the only logical thing that Walmart could do was throw out the entire stock of their boxes of sliced mangoes because they couldn't determine fast enough which grower or which consignment was the one that was actually mainly responsible. During the pilot, the amount of time it took to determine the provenance of the same type of food, the box of sliced mangoes, was reduced to less than 10 seconds. And this is how they were able to do it. Every aspect of the box of sliced mangoes, from the time it was grown to the time it was sold to the wholesaler, to the time it went to the warehouse of the distributor, to the time it went on the ship, and it was then it was unloaded on the port and then taken on a truck and brought to the individual Walmart stores. Every aspect of that was on the blockchain. And so you could tell whether those boxes were maintained at the proper temperature because those shipping trucks are all fitted with IoT sensors for pressure and temperature. And so if the temperature went above a certain amount for a certain amount of time, that is also being recorded. And you could tell which grower, which wholesaler, which distributor that box of mangoes actually went through. So that is the power of having something on the blockchain with IoT. So we have a lot of IoT sensors, and And we will talk about what makes blockchain so attractive in a bit. So, does anybody know how a blockchain actually works? Because if you all do, then I don't need to spend time on this side. But if you don't, I'll be happy to go through it real quick. Have you used a Google Sheet? It's an Excel spreadsheet equivalent on Google. Think of a blockchain like a Google Sheet, meaning multiple people can write to it. But once you write in a cell, nobody else can write in a cell. That's the key difference. So let's walk with that kind of a analogy. Let's quickly go through it. So it's a large open book where important information is recorded. Information goes into a block. Each page can represent a block, and it could have anything. It could be a single transaction, it could be a contract, it could be a vote, it could be any relevant data. So one transaction, one contract, one vote per block. Once the block is full, it cannot be changed. It's locked. You cannot write. So say, for example, if you enter $454.60 and then you realize, darn, it actually needs to be $461.95. You cannot go and change what you wrote. You can create a new block and say the actual number is 461, and it points to the old block saying that it replaces what I wrote earlier, but they both exist. That is the key. You can write it only once. Once it's written, it's locked, and the information inside cannot be changed. And blocks are chained together, but only after verification. Any new block needs everyone's approval in the chain to be accepted as the next block in the chain. And this verification process is crucial because it maintains accuracy and security. And so basically you have the block. Once the block is written, it's locked, and then it goes through the verification process, and then it gets added to the chain. And this is another crucial part. Everybody in the network has a copy. You cannot spoof. You cannot do any hashtagging. So each participant in the network has a copy of the entire chain, which means everyone has the same information, including its history. That forms its immutable audit trail. So let's quickly go through this here. One party wants some kind of a transaction. It could be a payment, it could be a vote, it could be a contract, and this is the peer-to-peer network. Individual people having their own copy of the entire of all the nodes. They have to approve it. Everybody has to approve it, and the approval process can take one of many algorithms, proof of work, proof of stake, and all that stuff which we're not going to. Once everybody has approved it, that's when it gets added to the existing blockchain. And only then that transaction which this guy tried to initiate is considered to be done. Any questions? I've gone at a very high level, but we don't have time to go. What are the benefits of a blockchain? Tampering with the past is almost impossible. And that's where the concept of immutability comes. Transparency. Everybody can see the information. There is no hiding. And this is the best part for me. It is trustless. There is no concept of a trust. You're not trusting some guy to do the right thing because there is no need for trust. And it is that very aspect of being completely trustless. It is what fosters complete trust in this network. Because you're not beholden to anybody, you're not expecting anybody to do the right thing. It is okay, you can trust it because everybody has got a copy of the entire network. Everybody can see the history, no issues. So it's an immutable, transparent, trustless network. And a blockchain is just a subset of what is generally called a distributed ledger technology. Blockchain is just one instance of it. AI plus blockchain is equal to what I like to call as accountable intelligence. Not just artificial intelligence. Now the artificial intelligence becomes accountable. We've already talked about this. How many people know what smart contracts are? A smart contract is a programmatic contract that is associated with a blockchain. The current contract terms, they are established, and you can have any number of events that cause the contract to get triggered. And when the contract gets triggered, it gets automatically executed. Let me go back to that example of IBM and Walmart. When the guy brings a shipment of the box of sliced mangoes, if the blockchain shows that at no point in time during the transportation was the temperature in the truck going above the acceptable range, then a smart contract will kick in based on that information and say he gets paid for. If, for example, the truck broke down and it was broken down for more than half an hour, and which means it caused the inside temperature to go up above the acceptable range, but it came back online after that half hour or that 45 minutes, and it's still okay, but we know that you had a broken down truck and this perishable foodstuff was not at the ideal range for about 45 minutes. You still get paid, but the program knows now you don't get paid 100%, you get paid only 85%. And no one can dispute the fact that you get only 85% of your charge because everything was on the blockchain for everybody to see that you screwed up or things happened beyond your control, but there was some damage to the merchandise. So that is the basic power of a smart contract. Nobody can dispute what a smart contract is doing because everything is on the blockchain and it is there for everybody to see. What does all this have to do with AI? Well, a blockchain can record the provenance and ownership of data used to train the AI model. You will know exactly where the data came from, which, if you guys have been paying attention to the news, has been a big problem for certainly big companies. Because it's not clear where where the data came from, or they've taken the data without proper authorization, and now they are in court. But if it had been on the blockchain, you will know exactly where it came from. And you will also be able to provide an immutable audit trail of all of the decisions that these AI models make. Now, that may not be a big deal if you're just using ChatGPT to do a marketing flyer or a business letter. But in the areas of healthcare and finance, being able to explain what the model did is crucial. If you're not able to, if your lawyer is not able to explain in court why your healthcare AI gave the particular diagnosis and caused the patient to die, then you shouldn't be using that healthcare AI. So you need to have model explainability, and a blockchain will help you do that because you can record every decision and all the outputs on the blockchain. And these two are my favorite. You can have decentralized AI training platforms. If you have a brand new Model X, which was trained by data from 100 contributors, but they all gave it the data in various amounts, each one of those people are going to now get compensated in proportion to the amount that they contributed to the model. And that is all dictated by the smart contracts. It knows that Joe gave about 40%, but Jim gave only 10%. So Joe is going to get paid in a higher proportion than Jim. And then you can also have a decentralized marketplace for AI models where people can actually judge the authenticity and performance of each model before they buy it, because everything is on the blockchain. So AI provides the brain, blockchain provides the truth. That's the key takeaway from this slide. Let's keep going. These are a few examples of AI and blockchain, and these companies are actually real companies, and unfortunately most of them are in the startup phase. But you are welcome to go look them up. I'm going to quickly go through a few data integrity and provenance. So if you have a Gen AI system that is producing content, you can use blockchain to verify the authenticity and origin. Decentralized AI, as I just mentioned, you might be using massive amounts of data from multiple sources. You need to know who contributed. Tokenized Gen AI, you want to say that I am the actual owner of this content because I created it. And the blockchain. And you can create, if you have an AI that creates synthetic data sets, those data sets can be stored and then transacted on the blockchain. And as I already mentioned, decentralized marketplaces for AI models, you can sell and buy these models in a decentralized marketplace using smart contracts. And of course, this is basically model explainability, which IBM has done a lot of work in blockchain. And then collaborative AI development, if you have multiple parties, multiple teams from different research organizations and companies working on an AI project, they all contribute both through the model and the data, then you could use a blockchain to track the contribution, make sure that the contributors are appropriately compensated. If there's only two companies that you go through after this slide, make it these two. They are doing some really good work, humans.ai and SingularityNet. But like I said, they are unfortunately still in the startup phases. But humans.ai is my favorite. We are actually building an IBC, an inter-blockchain communication bridge, which means because now people have different blockchains, what they have built let different blockchains actually talk to each other, which is fantastic. Okay, so blockchain can provide much needed guidance for AI. And AI is really the true killer app for blockchain. It's not Bitcoin. It is AI, which can be the true killer app for blockchain. Okay, now we get to the fun part. Any questions so far? Yes.
You described the blockchain, explain it, I understand that, but what is it a spreadsheet that sits somewhere?
It is the best way to think about it is a distributed ledger, which exists on every computer in a peer-to-peer network. If you remember,
file size that grows.
No, the actual number of blocks that get attached to the blockchain grow over time. Yes, it's all in software. It is basically a distributed software ledger.
That ledger is that.
In a way, yes, because you're not going to be able to store large amounts of data. Like, for example, if you want to protect a piece of art, which is a whole number of the megabytes, you don't want to store the entire piece of art on the blockchain, but you will store a hash function that points to the data off chain. So yes, so in that sense, yes, it is storing a lot of metadata to the real data. But if something changes, you will know that it has changed. Good. Okay. I promise this is going to be the only really technical slide, but it is important that we go through this slide. People know of a bit, the classical sense, 0 and 1. And how many of you have heard of qubits? All right, everybody has. Fantastic. Qubit is short form for quantum bits. Okay, and a qubit state is described by what is called a superposition by these quantum probabilities or quantum probability wave amplitudes. Yeah. And these are called alpha and beta. And this is the equation. This is the only equation on the slide. So just bear with me. So alpha and ket 0 and ket 1, as these are called, are the two basis states. Think of them as the quantum equivalents of what we know as 0 and 1. Okay? And these are actually basis vectors, which means they have both a magnitude and direction. And A and B, and I mean alpha and beta are actually complex numbers. So they are what are called the probability wave amplitudes. But for mod, the square of mod alpha is the probability of measuring 0 when you observe the qubit. The square of the mod of beta is the probability of measuring 1. Alpha square and plus beta square is always going to be 1 because the sum of the probability should always be 1. Okay? So, what does all this mean? A qubit or a quantum bit actually carries two probability amplitudes. They are actually called probability waves, which is why this whole thing is called a wave function. So think of these probabilities as waves. And the whole concept of superposition means both these probability amplitudes can exist at the same time. That's the concept of superposition. What is entanglement? Entanglement is a much more difficult concept. We will talk a bit more about it in other slides. But entanglement links these amplitudes across multiple qubits into one correlated system. And entanglement is what gives the exponential state space for a quantum computer. It is one of the most powerful aspects of a quantum computer that allows it to handle tasks which a classical computer is not able. And last but not least, you have interference. And interference is what manipulates the two probability wave amplitudes. Think of throwing a stone into a pond. Okay, so you have the waves, right? When the two peaks of the two waves come together, the combined peak is much higher. But if a peak comes in contact with a trough, the two waves are going to cancel each other. And that's basically the principle of interference. And interference, what it does is, interference makes wrong answers get cancelled and right answers get reinforced. So when the wave function finally collapses at measurement, you get the correct answer with high probability. If this is going above your head a bit, don't worry about it. We will go through all of it. But it is, for now, just keep these three terms in mind, because these three terms form the heart of why quantum computers are so much more powerful compared to classical. Okay? All right. Let's go through what are all the key differences between a classical bit that we all know and love versus this new guy called a qubit. Okay, so it's a basic unit of information. It can be 0 or 1, but here it's 0, 1, or both simultaneously because of this wave amplitude. How is it actually physically realized? Here, we all know how you can get a classical bit. It can be a transistor voltage, it can be a magnetic domain, it could be an optical disk fit. But here, it has to be an electron energy level, or it could be a superconducting circuit, individual atoms at incredibly low temperatures. And in certain physical qubits have to be kept at temperatures colder than outer space. Otherwise, they won't exist. Where does it live? Well, we all know that we all have phones which run on the classical bits, and they all do fine at room temperature. Whereas these guys need specialized cryogenic chambers, vacuum traps, optical circuits in highly controlled environments. What is the temperature requirement? These guys require near absolute zero, like close to 273 degrees Kelvin, which is very, very cold, colder than outer space. Information capacity. One bit is one value. Here, n qubits can have 2 to the power of n simultaneous values, which means 20 qubits can represent 1 million states at once. That is the result of what is known as entanglement, which we get into in a bit. And that is where it gets its power. N qubits, you get 2 to the power of n simultaneous values. Can you actually copy our classical bit? Of course, but this has to follow the rules of quantum physics. You cannot copy it. The very act of copying one qubit will actually cause it to get destroyed. So you cannot, and there is a thing called the no cloning theorem. We don't have time to go into it, but that's basically what it is. The error rates, we have done really well to bring the error rates to a really low number. Whereas here, the error rates are very high because a qubit will rapidly degrade. Yeah, Vijay.
But yeah, actually, because the bit can be copied and qubit, there's no copy, but it creates a copy, right?
No, it doesn't. No. I will tell you what happens when we get that. Classical bits are very robust, as we all know. These are extremely fragile. A single stray photon or even a vibration is going to cause the whole thing to come crashing down. And we have gates that operate in picoseconds. These also have gates, but they operate in a much larger scale of time. Okay. What are these best for? Of course, we all know this: text, video, databases, browsing. These, on the other hand, are really good for logistical optimization, for molecular simulation, cryptographic analysis, and supercharged machine learning. Quantum computers are going to make machine learning go really fast. Very wide a bit. And the level of maturity, well, we've been doing this for over 70 years. We know how to do this. These are pretty early stage. The largest systems have only about 4,000 physical qubits. So we are still many years away, but not that many years away. As we'll find out. Okay, let's keep going. So here I'm going to talk about the 4 key phenomena that distinguish quantum bits from classical bits. And those are superposition, entanglement, interference, and the bad guy, equivalence. Okay? So what is superposition? A qubit can exist in multiple states simultaneously until it is measured. And one thing you have to keep in mind, or try to get your head around, the very act of measuring a qubit will cause it to collapse. So you don't actively measure the value of a qubit. And everything. What happens is the act of measuring a qubit causes it to become either 0 or 1. And at that point, you have an old-fashioned bit, and you lose all of the advantages of it being in a 0 or 1 at the same time. So what is a simple simple analogy here. A coin spinning in the air. Until it lands, it could be heads or tails. You don't know which. Until it lands, it has maybe an equal probability of being heads and an equal probability of being tails. So here, entanglement is a bit more difficult to understand, but this analogy is actually quite accurate. A magic dice, if you roll one in New York, the other one, as far as in Tokyo, will always show them matching hits. Hold on to the thought for it. I see a lot of eyes widening in the room. And the interference, noise cancelling, think of these as noise cancelling headphones for computation. They amplify the signal and they reduce the noise. And then decoherence is basically things that could go wrong. If when you're trying to spin a coin, somebody comes and knocks the coin out of your hand, guess what? You have to start all over again. So this guy is always the bad guy. He's going to cause bad things to happen in a quantum computer, but it's a natural phenomenon that you can never get rid of. You can only try and make it less or try to minimize the effects. Are all of these phenomena natural or engineered? They all are natural. But here's a spoiler alert. Each one of them can be controlled by circuitry or based on how the qubits are created. You can control each one of them, and how well you control them is going to determine what you can do with a quantum computer. The only one that is not that can't be fully engineered is the bad guy, and if the decoherence is the enemy of quantum computing, it cannot be turned off. It can only be minimized. And right, so as I said, you have the notion of quantum gates. C naught is a short form for a controlled NOT gate, and it's a type of quantum gate. So what is the effect of these quantum computer phenomena on what is the effect of these natural phenomena on quantum computing? Superposition is what enables parallel exploration of all possible solutions at once. But then entanglement takes it a step further, because now it increases your state space exponentially. N qubits, it represents 2 to the power of n correlated states. And interference is what brings it all together. It all steers it towards the correct answer. Without interference, these two things are not going to be of much use. And then decoherence is what causes the entire quantum computation to actually get collapsed, so that there's superposition and then it breaks entanglement. When does it happen? You want to start superposition or want to create superposition at the start of a quantum algorithm. And you have to maintain it until measurement. Entanglement you create during the algorithm execution, when the qubits need to work together. Interference is what happens throughout the algorithm execution via carefully sequenced gate operations. You think of what you do when you have a chip, which is on silicon. You are actually having to program the chip for it to do something really useful. Same principle here. You're programming a bunch of qubits to do what you want it to do, but you're just using different types of gates, and you have to operate at a very cold temperature in highly controlled environments. And then decoherence is something that happens continuously. You are constantly fighting the battle against decoherence, because heat, vibration, increase in temperature, or any kind of shaking or cosmic rays, all those things will cause your whole quantum qubits to fall apart. What is the control mechanism? Quantum gates. There is a type of gate called the H gate or the Hadamard gate, which actually starts off the whole process. You have the C0 gate, where you can control entanglement, and then you have the gates sequences which are chosen to create the desired interference pattern. Unfortunately, this cannot be controlled. You can just try and stay clear of it, or you can try and mitigate it through isolation, cooling, and error correction. And this decoherence aspect is why there is a big difference between physical qubits and what are called stable, error-corrected, logical qubits. Right? Now, let us look at this from the view of, let's try and explain this in more simpler terms. And I'll start off with the simplest kind of analogy. And since we are in the state of Nexus, superposition, think of it as something that loads the gun. Entanglement aims the gun. Interference pulls the trigger. That's all it is in the terms of quantum computers. And what is decoherence? Decoherence is the guy who comes and knocks your hand off while you're trying to do these things. So that is what is one way to look at quantum computing. Now, move this guy all the way up off my screen, Chris. Oh, there you go.
Yeah.
Okay. I like this analogy a lot better because it's actually not as violent. Imagine you're in a room full of people, all of whom are shouting answers to a math problem. Okay? Superposition.
What you did to show?
Yeah. It's the same thing.
Okay.
Yeah.
I just want to make sure you.
Right. So, imagine you're in a room full of people, all of whom are shouting different answers to a math problem. Okay? What is, in that context, what is superposition? It just means that all those answers, they all exist at the same time. Okay? And in this context, what is entanglement? Entanglement means that all the people in the room who are shouting these answers are now linked because what one knows, the others in the room, they come to know instantly. Because the guy is actually shouting out the answer, they can hear it. So whatever he knows, all the others in the room know. That is entanglement. Interference is the acoustic engineer who's trying to amplify the voice that is shouting the answer, which happens to be the right answer, and trying to cancel out all of the wrong ones. Because the acoustic engineer kind of knows what the right answer is. So he's trying to amplify the voice or the voices that is shouting out the right answer, and canceling out the noise from the wrong ones. So that when somebody's actually paying attention and listening, you are able to hear the answer which happens to be there. I don't know whether that kind of analogy helps you guys to understand, but it definitely helped me. So let's do one more analogy and then we have to move on.
Just got a question on that.
Yeah.
Everybody's in the room, so it's easily networked. Going back to your previous analogy that the answer that's in New York is also known in Tokyo at the same time, that makes the assumption that there's a network in place.
Right. Yes. Yeah. I mean,
So they're two separate computers. So there's a network between all of them.
I wouldn't. Okay. The point is that it is possible to actually have the state of a quantum computer be propagated to other, the state of a qubit to be to be the best word to use it is to say it's correlated, because you cannot say I am doing any kind of measurement, because the very act of you trying to measure the state is going to cause the whole thing to collapse. So you can't say that you're trying to measure.
Not instant.
No, it's not. It's not. Okay, because entanglement is basically, I mean, it's basically what one qubit knows, all the other qubits also know. Yes, I mean, and here's the fun part. People know now how to create entanglement, how to control it, but there is still very limited understanding as to why it happens as a natural phenomenon. But it happens only when you are in the quantum state, which is like based on what technology you're using, you have to be at really low temperatures, or you have an ion that's trapped between two fields, and so on and so forth. So it is easily controllable and easily designable, but there is not much information as to why the heck it happens, because it happens when these things are in a quantum state.
That's where we get with the concept of quantum networking, which they haven't quite figured out yet.
Yes. Okay, one more. Superposition is basically loading all possible answers into the quantum system. You think of it that way. Entanglement links the qubits so they are exploring the solution space as a whole system, as a unified whole system. Interference is guiding the system towards a right answer by canceling all of the wrong paths. And decoherence is the villain, constantly trying to collapse everything back to becoming a classical system. I don't know if these analogies have helped you any, but they definitely helped me, so I wanted to share them with you. Okay, let's move on. Oh, did I lose focus? Is that right? There we go. Okay. One more slide on the different kind of that time scale. This usually is microseconds to seconds, depending on the qubit type. And entanglement is actually persistent. Once you create entanglement, it stays until either the decoherence hits or you actually make a measurement. Interference is nanoseconds per gate operation, and this one is microseconds to minutes, based on which technology you're using. And we will get into what the different technologies are in a bit. So what are these, what is the advantage you get from superposition? Very simply, parallels. The fact that a single qubit can be in a 0 or 1, that gives you built-in parallels. Entanglement, it gives you exponential scaling. N qubits gives you 2 to the power of n states. That's huge. But none of these two are going to mean squat if you didn't have interference. Because interference is the one that gives you computational directionality. You have all these things which are operating in parallel, and you have this exponential space, but now you need to get to the right answer, which means you need to kind of blow away the wrong paths and focus on the path that so in a lot of ways, each of these guys needs the other. If all you had was superposition, and entanglement, okay, maybe need all three. But what you don't need is the last guy. What causes these things? Quantum systems have no definite state until they are measured. That's a fundamental property of nature. And entanglement actually follows the conservation laws during particle interactions that create correlated quantum states. The wave nature of quantum particles. If you go back to my slide where you have the probability wave amplitudes, because those probability waves again are complex numbers, they could be a positive or negative. So you could have interference that is considered to be constructive interference, or you could have interference that's considered destructive, meaning the two probability waves will cancel out each other, or they will enhance each other. Yeah, Jim.
So the quantum computing computer, at that point, the qubit is destroyed for 3 seconds.
The qubit will, if measured, the qubit will have to pick a state. It will either fall down to a 0 or a 1, and at that point, it's no different than a classical. Right. Okay. And any interaction with the environment causes the quantum information to be cut. Are all of these required for quantum computing? Absolutely. You don't have supervision, you have no quantum advantage. And algorithms like Schrod's algorithm and Grover's algorithm, they require entanglement. Without interference, you're going to get just random results. We definitely don't need this, but we have this all the time because of the environmental issues. What happens without it? Without supervision, you don't have a qubit, you have a classical. Without entanglement, each qubit is independent of all the other qubits. You're not behaving as one unified system. You no longer have an exponential space because each qubit is acting independently. And if you don't have interference, you can have these two guys, then you're basically going to get a random output because you're going to get both right answers and wrong answers. And you won't be able to make it. People at IBM and Google especially wish they didn't have this guy, but he's there all the time because of environmental issues. For a real world, must be created and maintained long enough. It must be very precise. Your algorithm success depends on how you do your interference. And this is the primary cause of errors. This is the reason why we need to have error correction. Okay. I think we are going to have to speed up a bit. I have until 7:45, right?
Correct.
Okay. I just want to give you guys a flavor that not all qubits are built the same. There are different technologies to actually do the physical realization of a qubit. The one that is being used by IBM and Google is what is known as a superconducting qubit. We have tiny aluminum and niobium rods circuits which are cooled to milli-Kelvin, and the quantum state is encoded in the charge or the magnetic flux. Trapped ions, these are small individual atoms of equilibrium that are stripped off that are missing one electron, and they are actually suspended in midair in an electromagnetic field. And the state is encoded in electron energy levels. You also have photonic qubits, and you also have topological qubits. This is the one that has been proposed and built by Microsoft. And where do these qubits live? This was a question I had while doing these slides. By the way, this is the first talk I am giving on quantum computing. So I've had to learn on the fly. These live on a chip inside a dilution refrigerator. In this case, they are suspended in ultra-high vacuum above a chip. It's so cool to hear absolutely see it. Here they are optical circuits, and here superconducting on a nanowide chip inside a dilution refrigerator. What is the operating temperature? 15 millikelvin, colder than outer space. This is a room temperature vacuum chamber, but inside it you have little laser cooling, and these two have those. Gate speeds are really fast, slow, microseconds to milliseconds. Let's keep going. The quality of the qubit. How long does a physical qubit last before it collapses? That is a big deal. And with superconducting, it's only microseconds. They're working hard to increase the lifespan of the qubits. Superconducting. These guys are the best so far because they actually last seconds or minutes. They have the best quality of any platform. Here, the photon loss is the main challenge. Microsoft claims that these can last really long, but they are in very early stages. And the error rate is quite high here, which is why you need the correction. These guys is actually quite low, and they're doing really well. And it's kind of moderate. In theory, it should be really low, but once again, this is the very early stages for the Majorana platform. This is an example of a cryogenic quantum chamber. You have these circuits, and all of these circuits inside, the temperature is maintained at 15 degrees mean Kelvin.
How big is that?
This one is, I think, close to a 3 or 4 story building. If you see the entire one, it's really big. But the Google Willow chip was able to recently solve a complex problem that would have taken a classical computer 10 septillion years. We solved it in 5 minutes. That is the power of the machine. Okay, so these are actually being fabricated like classical chips. IBM and Google are reporting 1,000 plus qubit systems. These are a bit more harder to scale. These are promising. This is potentially excellent. But once again, a lot of it is vaporware. And their qubit is only, their quantum has only got 8 qubits. So they have a long ways to go. In terms of maturity, these guys are the most mature, followed by trapped ion. At IonQ, how many of you were at the Texas Quantum Economy Conference this past weekend? Only 2 hands, I see. Yes, because I didn't see any of you guys. You missed a really great presentation by the guy from IonQ. It was also heartening for me to be at the presentation because I am long on IonQ stuff. Completely unnecessary piece of information. Okay, the key advantage: speed and manufacturing, highest accuracy. These guys are very fragile. Decoherence happens in microseconds. They don't last very long. Slow gates, hard to scale, photon loss. Who's doing all this? IBM, Google, Rigetti, IonQ, Quantinuum, and all these companies. So they are companies. The point of all this is there are companies actually building quantum computers, and they are getting moderate success over various levels of qubits. This one.
All of this is based on basically binary. You're talking zeros and ones, and 0 and 1 at the same time. What would happen are there ternary quantum computers? Are you dealing with 0, 1, and -1? And it could be all the same because it would wind up being
that is a much
multiple of everything.
That is a much more the field of pure research, whereas these are actually out there. They're actually solving real problems.
There is no ternary quantum.
Not that I know of, but that doesn't mean what. It might. Okay, so what are the use cases? Near-term optimization, chemistry simulations, high precision, and all this other fun stuff. Okay, why quantum matters for business? Why are people so excited about it? Because drug discovery normally takes 10 plus years, billions of dollars. Quantum can simulate molecular behavior from first principles, something classical computers cannot do. AstraZeneca plus Amazon and IonQ, they actually have quantum accelerated drug synthesis workflows. These guys have done a lot of work finding out the structures of different molecules. This will have a transformational effect on the drug discovery market. The chemical space of potential drugs is estimated at 10 to the power 16 molecules. No classical computer can get to that, ever. Quantum computers can. And because they are able to model quantum and mechanical interactions at the molecular level that the machines that we know of today just cannot. Quantum threat. What is it that I was talking about in my abstract? Everything online right now we take for granted is protected by public key cryptography. RSA 2048, ECC, ECDSA 256, banking, email, medical records, government systems, IoT devices. RSA security, RSA 2048 relies on one assumption: factoring very large numbers is impossibly hard for classical. The whole point of RSA 2048 is they have a 2048-bit prime number. Trying to find the factors of that larger prime number is beyond the capability of classical machines. And that's what they are banking on. And that's why they've been doing so well. RSA 2048, until recently, was the encryption used for blockchain. Shor's algorithm, Peter Shor in 1994, he came up with a quantum algorithm that can factor large numbers, large prime numbers. And he showed, and no, it wasn't he, but Stefan Beauregard showed in his paper that you needed just 4,099 stable qubits to break RSA 2048. That is where things get scary. And he used this formula, 2n plus 3. If the number of the bits in the prime number was n, you just needed 2n plus 3 logical qubits to break that, to be able to find the factors of that n-bit prime number. Grover's algorithm, which came out in 96, it is another for quantum algorithm. It said that an unstructured data set of 9 items can be searched in square root of n steps instead of n steps. That's a quadratic improvement. That is huge. And what that means, so an AES 256 security goes from 2 to the power of 256 operations to 2 to the power of 128. That is weakened by half, but 2 to the power of 128 operations is still astronomically large. So we are okay there. AES 256 is safe. It's going to be a while, maybe a few decades or a few tens of decades before that is cracked. When quantum computers become powerful enough, meaning when they have enough number of bits, all these guys are gone. All these encryption technologies are history. And therein lies the rub. Q-Day, or Y2Q, is the day a quantum computer can break RSA 2040. Current estimates are it's going to happen around 2030. Cybersecurity Ventures predicts that Y2Q will be on or around January 1st, 2030. In the largest scheme of things, ladies and gentlemen, that's tomorrow. That's not very far away. This is just not one for forecast. IBM, Google, Microsoft, PSI Quantum, and other government roadmaps all converge at the same time. Y2K. I think there are a few people who are old enough to know what Y2K was. Yeah.
I'm not raising my hand.
You went for 1K.
I know. Y2K cost was $308 billion. Y2Q is going to make them look like chump change. And here's why. Y2K was a known date, a known fix. You had to change the format of the date to include 4 digits for the year and you're done. So people knew what to do. It still cost $300 billion. Y2Q is an uncertain date with a massive fix. What is the fix that we have to do? Replace all cryptography. So you can imagine what we are talking about. The convergence of industry roadmaps around 2030 needs prudent organizations should be starting now, or should have started last week or last month. Yes, please.
That doesn't mean people are just recording everything. There we go. Thank you.
Way ahead of you. No. Thanks for that. And adversaries are adopting a harvest now, decrypt later approach. And this is actually happening. Cybersecurity firms are actually tracking this, and this is actively happening. They're already intercepting and stockpiling encrypted data, even though they don't know what the heck to do with it now. They're just hoping that quantum computers will hand them the keys in about 4 short years. Leave it now, wait for quantum computers, decrypt later. And what are they going after? They're going after government communications, financial data, health records, trade secrets, IP. This is not hypothetical. Intelligence agencies worldwide are actually tracking this, and they have confirmed this. The US Federal Reserve has studied this list. Data stolen today, which has a 10-year shelf life, is still going to be decryptable during its valid lifetime. Just think about that. It's all of our data, all of your bank records, all of your tax, everything. HMDL attacks, unlike any other kind of attack, are completely silent. You don't know it's happening. There is no flashing screen. There is no, you can't get into your machine. There is nothing. It's happening in the background. And adversaries are quietly exfiltrating data, confident that quantum will handle the keys. If your organization handles data that has long-term value, patient records, financial data, governments, the threat window is wide open already. What's vulnerable? More than you think. And leading the pack is IoT. IoT devices, billions of devices worldwide with embedded cryptography cannot be easily updated. There is no path for a firmware upgrade for most IoT devices. Because we thought, hey, RSA 2048, we are good. Blockchain networks, Bitcoin, Ethereum, all of those other meme coins, they're all in danger because they're all using now ECDSA 256. They're all directly vulnerable to shows like that. Enterprise systems, VPNs, legacy systems, long refresh cycles means that you may have only 1 or 2 upgrade windows before Q-Day. Every connected link in the supply chain is an attack surface. Blockchain is especially interesting because its security model is cryptographically native. It is the encryption. If ECDSA fails, it falls, blockchain falls. And here's the tough part. You can replace maybe the blockchain cryptography with post-quantum alternatives, but that makes your encryption signatures between 4 and 32 times much larger. That's going to impact efficiency. It's going to impact the time in which it responds. It could have an effect throughout, and it will cause serious scalability issues. IoT, as I mentioned earlier, is equally concerning because many devices have no mechanism whatsoever. There is trouble in paradise, ladies and gentlemen, for all the for all the crypto bros in the audience, you don't have to raise your hands, but 25% of the supply of Bitcoin is exposed because it was using the early addresses, which actually put your entire signature, your entire public key on the chain forever. And once you put something on the blockchain, it cannot be changed, right? So it's there forever, as I mentioned earlier. Now you know why I spend so much time giving you the basics. So now you understand. And it's even worse in Ethereum, because even today, the way the address model works is, if you have any kind of transaction on the Ethereum network, your public key is exposed forever. At least with blockchain, you can actually do a refresh and have a new key for each new transaction. With these guys, it makes the problem even worse. And even though these guys use all these other things, each one of them is quite small, so they are an easy target. The day you have a quantum computer that's capable of breaking these guys, the entire thing falls on its face. And Ethereum has got other things which make it even more vulnerable, but to their credit, they are actually springing into action. They've just sprung into action. They actually have a quantum-resistant Bitcoin improvement proposal, and this is a multi-year community migration. The only problem with this, they started quite late. It's going to take them 7 years to migrate all of the Bitcoin blockchain to the quantum resistant. 7 years is, if you were paying attention to the previous slide, it's kind of 2 years after January 1st of 2031.
Who's they? Who's going to do it? I mean, Bitcoin is
right. And so basically there is an entire, I mean, the entire Bitcoin community is going to have to make an upgrade to all of that. They're all the nodes.
I can tell you what is the impact? Use a full range.
What's that?
Things like house bed gloomy and gloomy.
Yes, it is. It is doomy and gloomy if people don't take any action. But the fact of the matter is, these guys are taking action, as are these guys. And now they say they are fairly confident with this hard fork plan. When they say the hard fork, for guys who are into blockchain, you know, you actually fork the entire chain, and then everything that's added goes into the new fork. And Vitalik Buterin has said that with this hard fork plan, it's executable within days. So the moment there is a viable quantum machine, he can put this plan in place, and he thinks we will all be safe. That's the claim.
But Bitcoin, 7 years, you said?
It was the view of one of the guys who said that it might take as long.
We're talking about 1.5 trillion assets,
Which could be,
compromised overnight.
yeah.
It sounds like too big a risk.
And based on your perspective, the cruel or delicious irony is, they could have moved from RSA 2048 to RSA 4096, or they could have even moved to RSA 3072, but they chose to move to ECDSA 256 because it was more efficient. Handshakes and all certain things. The problem is that efficiency advantage is now a huge quantum liability, because ECDSA is shorter key, means that Shor's algorithm requires fewer logical qubits to break the encryption than had they stuck with RSA 2048. So they've kind of brought this upon themselves by moving to what they thought was a more efficient algorithm that gave them comparable security, then in reality, now they are exposed even more. Yes.
Yeah, do they have any regulations for this from the government side? Because as I see, because even the personal devices, whatever the mobile, everything is getting crashed, right?
Yeah.
So,
Yeah. Well, to answer your question, NIST has released the 3 finalized PQC standards. PQC stands for post-quantum cryptography, and these are all available to be used now. And the directive is start using them now. Don't wait.
There's also quantum resistant, like.
Yeah. So from now to 2030, phase out for vulnerable encryption methods. By 2030, all algorithms that are using the old security will be deprecated. And they're not joking. If you are any kind of financial or government organization, you will not be able to use the old algorithms after 2035. And there is actually a list document that lays out the timelines. Here's what people in Canada are doing. They have a very firm migration plan. And the first wave of binding PQC compliance requirements are going to be out this year. People are taking this seriously. I'm almost done. The 3-day convergence, as we saw, PC can be used as a guardrail for AI. AI optimizes blockchain. Quantum accelerates AI training and inference. Blockchain, AI can be used to detect fraud on chain. And as we just saw, quantum is threatening blockchain, crypto, PQC protected. AI helps to design quantum algorithms. The blockchain can log quantum computations. AI plus blockchain, mutual reinforcement, trust plus intelligence. AI plus quantum. Quantum accelerates what AI does best, optimization, pattern recognition. Blockchain plus quantum. It is both an existential threat and one of the biggest opportunities that you can come across. These are some examples of real-world convergence. I'm going to just go through them really fast since we're out of time. But you can look these up. These are all actual companies and actual efforts that are actually combining 2 or 3 of the 3 technologies. These guys actually have 22 satellites in orbit, which are quantum resistant from the ground up. And this guy, Falcon. They're all post-quantum. So what's the roadmap? We know that blockchain is already going beyond just Bitcoin and other cryptocurrencies. NIST has already taken the lead and they've published 3 standards which you can start using today. In the next few years, you're going to see these things happen. The HMDL attacks, harvest now, decrypt data are only going to get worse. Then you have cryptographically relevant quantum computers emerge. And I had to add this line of organizations that didn't migrate face catastrophic damage. And as one researcher said, people who wait may face unimaginable financial security and technology. Well, what you can do, conduct an audit. Perform a risk assessment if your firm is using data of long-term value. Try to understand what the long-term exposure is. There are automated tools that help you do an audit of your cryptographic systems. Have a PQC migration plan. Build crypto agility. Design systems that can swap out one cryptographic algorithm to another without blowing everything up. Start implementing the NIST standards. Step 1 is where most organizations fail. They don't even know where their cryptography lives, but you can have automated tools that scan crypto. And security is a good thing to have. Don't panic, but don't wait either. Don't assume that your vendor is going to solve the problem for you. You have to go ask him. You start with the inventory. You engage with the vendors. Demand PQC roadmaps. If you're having a cryptography vendor, ask him. Ask him to first expand the acronym PQC. If he has problems, go find a different vendor. Use the migration as an opportunity to help improve overall security, to make AI part of the solution. A number of AI-based tools that can accelerate cryptographic discovery and risk assessment. The smart approach is systematic: inventory, assess, plan, pilot, deploy. AI, blockchain, quantum opportunity for the business leaders. Use blockchain to create audit trails, explore AI-powered compliance and fraud detection, evaluate where transparency gaps. For tech leaders, implement PQC now. Don't wait for the next refresh cycle. Test hybrid classical quantum workflows. Build crypto agile architectures for everyone. The convergence is an opportunity, not just a threat. All of these technologies are moving from being on paper or labs to the real world. You are never too small to at least start thinking about solving. When I say never too small, I meant as a company. Oh, I'm a startup. I'm interested in getting out my MVP. Well, you need to be thinking about this as well. Key takeaways. AI is powerful but needs transparency. Blockchain provides it. Blockchain creates immutable trust, but its cryptography is about to be shot to bits. Quantum computing will break today's encryption. The timeline is 2030. NIST has a bunch of standards. Harvest now is a real thing. Harvest now decrypt data is a real thing. Convergence is of all three is the biggest risk and the greatest opportunity. AI needs trust. Blockchain provides the trust. Quantum is threatening the trust, but it also enables entirely new capabilities. Organizations that navigate this convergence will have profound competitive advantage. And no talk is going to be complete without two shameless plugs. My next AI workshop is on March 28th. There's a scan the QR code if you're interested. And as some people ask, this is my gourmet chocolate truffle business. It is a real business with a real online store. Scan the QR codes. And last but not least, thank you all for paying attention. We have time for questions.
I just want to say one thing, if I may. I'm not very technically advanced, but I'm feeling a professional services. So every day I wake up and on LinkedIn, there's something new about learning AI. So I didn't know anything. I met Yeshwant at an event. I decided to invest in myself. I spent some money. I went on the first Gen AI course last August. And I'm this way absolutely blown away. And all of a sudden, I'm using tools I've never used before. Because he had shown me how to make it very simple, talking about this stuff. And all of a sudden, my life has become so much easier. And just now in January, I attended another course. It was the Injecting, right? And again, it was a one-day seminar, one-day course, absolutely brilliant. I've actually now created virtually assistants in now. This is a guy who's not very technical. But what I'm trying to get across, it's well worth the investment to get out of this course.
Thanks, Pankaj.
That's what I just thought.
Yes.
So let's say they build a quantum computer in. Doesn't mean that everybody will have it, right? The bad guys will not have it. Think about IBM Deep Blue. That was only because it played Gary Castro and doesn't mean that I suddenly have an access to it. Why don't we just stop the quantum computer falling into the wrong hands? Don't sell it to them.
No, but
Don't sell it to the government.
that's like saying we shouldn't have any more technological advances because the bad guys might also have. Because there is a tremendous amount of work being done, not just by IBM and Google, but a lot of companies. Just a really fantastic work on the machine.
So it's like maybe not Korea or something.
Right. I mean, in fact, I didn't mention any of the Chinese firms, but they are actually working under the radar. Word on the street is they might have quantum computers with more number of stable logical qubits than both IBM and Google.
With our military, do you think they're doing something, or are they just, is IBM and Google as far along in the US as it is?
No, I mean, IBM and Google are using one type of physical qubit technology, but as I showed in the slides, that is not the most stable. Because they're using the superconducting qubits, and that is a lot more finicky than track ion. I'm a big fan of ion Q, and that's not just because I have their stock. I own their stock because I'm a big fan of ion. That makes sense. Because their technology track ion, their qubits are actually, they remain stable for the longest. They don't have as finicky temperature requirements, because all the everything happens inside a constrained light. So the vacuum chamber itself is going to be at long temperature. It's inside the vacuum chamber. So, but it is still the early days. I mean, it is entirely possible that IBM and Google will find ways to improve the stability of this superconducting qubits and go way past ion qubit. That is entirely possible.
What about tropical which Microsoft uses? What about the tropical one which Microsoft?
It's not tropical, it's topological.
Oh, topological.
Yes, and that holds a lot of promise. Like the technology behind it is under a lot of dispute because Microsoft has made some really tall claims. But at the end of the day, their quantum computers only 8 qubits. They've made claims like you could go up to 1 billion qubits still to 8. And people are saying, okay, sure. That's where the things are. Yes.
Do you personally believe Microsoft's claims thus far?
I was quite impressed with that paper, but I have since learned to say that let's wait and see who wins. But Microsoft has been doing some really good work. But if you read that paper, it is the theory behind what they are saying, it will make sense. I would encourage you, if you are interested, go Google it. Majorana won. And their paper is really good. But the proof of the pudding is in the eating. They actually have to show that architecture is going to be stable.
Or is it Majorana one?
Yeah. MAJ. I think you had a question, sir? You raised your hand?
Yeshwant, are you gonna be able to stick around? for a
Yes,
bit?
yes, yeah.
Okay. Thank you very much.
Oh, yeah.